Hello everyone. Today we will be discussing about basics of seismic wave propagation in rock physics. The seismic waves are generally a fundamental carriers of information about the Earth interior. That means whenever an earthquake occurs, or whenever some kind of explosion or any man-made energy disturbances are created, they are used in geophysical surveys, and these seismic waves propagate to the earth material, and this will explain about the interiors of the earth, the manner in which these waves travel. Like you say, they can reflect or diffract or refract or even attenuate. That depends on the physical and the elastic properties of the subsurface. So understanding the seismic wave propagation is not only in seismology, where it can also be used in earthquake hazard assessment and also earthquake hazard monitoring, but it is also a part of applied geophysics. Here in applied geophysics, we are focusing on petroleum exploration, mineral exploration, groundwater studies, and also geotechnical investigations. So in this video we will discuss about the overview of basic seismic wave propagation, and in this we also cover different types of seismic waves and their physical laws and their behavior in different geological media. So first we will discuss about the seismic wave definition. A seismic wave is generally an elastic wave that propagates through the earth as a result of sudden release of energy. When it comes to the natural sources, it is earthquake or volcanic eruption, and if it is artificial, then it is either by explosion or any kind of vibrosis when seismic surveys are conducted. So if we discuss about the energy sources, seismic waves are generally generated by two kinds of sources. One is the natural source and the other is the anthropogenic source. So even when a vehicle movement can be recorded in a seismic equipment. So this is about the source. Now when we discuss about the elastic medium, we are discussing about the seismology. So it depends on the earth crust, because earth crust acts as a elastic medium. So the medium is continuous and isotropic. That is one of the key assumption. And the second assumption is stress is proportional to strain, which is mentioned by the Hooke's law, and small deformations are to be considered, and then only we can make earth crust as an elastic medium. Next we will discuss about the seismic waves. So in these seismic waves, they are into like body waves and surface waves. So body waves means they are traveling through the earth's interior. In this we have the primary wave, which is like also called as P wave, and this travels in the form of compressions or longitudinal waves. Particles in this medium move back and forth in the same direction as the wave is moving forward. These are like the fastest seismic waves, and thus first to arrive at the seismic stations. So when you take a seismic station, when an earthquake hits the receiver, first arrival wave will be the primary wave or P wave. After that, the secondary wave will touch. So based on the distance between the P wave and the S wave, we can estimate the magnitude and the location of the earthquake. And now we are discussing about the secondary waves. They are also called as shear waves or transverse waves. In these waves, the particle movement is perpendicular to the wave propagation direction. The thing is, they cannot propagate through fluids like liquids and gases. And next comes the surface waves. So these surface waves, usually they propagate to the earth's surface, usually cause the most damage during the earthquakes. And after that you can see in that you have the Rayleigh waves and the love waves. The Rayleigh waves are elliptical particle motion, and they are similar to the water waves on the surface. And comes to the love waves, they are purely horizontal transverse particle, usually caused by large horizontal ground shaking. Now we'll discuss about the physics of the seismic wave propagation. First thing is the elastic wave equation. Here the propagation of the seismic wave in any elastic medium is governed by the elastic wave equation derived by the Newton's second law and also the Hooke's law. And then the reflection and refraction, this is based on the Snell's law. When the seismic waves encounter an interference between two media with different velocities, part of the energy reflects and part of the energy refracts. That is the Snell's law. And when it comes to the attenuation, seismic waves lose energy as they propagate. This is due to the geometrical spreading, that means energy distributed over a large area, intrinsic absorption, that means conversion of mechanical energy into heat energy, scattering, that is redirection due to the heterogeneities. The other thing is dispersion. Surface waves, especially the Rayleigh waves and the Love waves, exhibit dispersion. That means their velocity depends on the frequency. This property is exploited in surface waves, that methods to infer the subsurface layering. So when we discuss about the factors affecting the seismic wave propagation, they are the elastic properties, heterogeneous properties of the earth, anisotropy, frequency dependence, and we'll discuss one about the other. When it comes to the elastic properties, velocity increases with the higher rigidity and lower density. Fluid cannot transmit the S waves. In case of heterogeneity of the earth, seismic velocities vary with the depth, lithology, porosity, saturation and fracturing. Interfaces produce reflections used in seismic exploration. When it comes to the anisotropy, in anisotropic media, velocity depends on the direction of propagation. This is common in shales or fractured reservoirs. And the frequency dependence is also very important. Higher frequencies attenuate faster. Lower frequencies penetrate deep but provide low resolution. How the seismic wave propagation takes place in the earth? When you take the first layer, the crust and mantle, P waves and S waves travel at increasing velocity with the depth due to higher pressure and rigidity. Discontinuity such as Moravec discontinuity or MOHO causes a sharp velocity contrast. Outer core, P waves slow down drastically, but S waves are absent in the fluid medium. This generates the S wave shadow zone. When it comes to the inner core, P waves accelerate again. Some S wave propagation may exist due to the solid state of the inner core. In the seismograms, if you see, seismograms are something like a recording devices that record the seismic waves and shows the characteristic arrivals. That means P waves arrive first, S wave comes the next, and the surface wave comes the last. But these surface waves have the largest amplitude. If you take the applications of the seismic wave propagation, we can use these for many purposes, like earthquake studies, locating the epicenter and the hypocenter, studying the fault mechanics, estimating the magnitude and energy release. The same way, these seismic waves can be used to study about the Earth's internal structure. Seismic tomography uses a travel time of seismic waves to image mantle conventions, subduction zones and plumes. Discovery of Earth's core and inner core was also achieved through these seismic studies. When it comes to the exploration geophysics, hydrocarbon exploration relies mostly on the seismic reflection surveys. Subsurface layering and traps are mapped using the wave reflections. Refraction surveys are used for shallow engineering and ground investigations. When it comes to the engineering applications, site response analysis for earthquake resistant designs, microzonation of seismic hazards, non-destructive tests of concrete using the ultrasonic waves can be used.